Well, this is an interesting little problem here where we are going to need to use, in this case, an exponential growth equation to build an exponential model and then be able to graph that to make a prediction. So it says use the data in the table, and assume the population of Miami-Dade County is growing exponentially. And it doesn't tell us whether it's continuously or annually or what. But let's first kind of focus on what data we've been given. And I see between the years 1990 and 2000, well, how many years is that? That's 10 years. So 10 might be my time. And then I see that it starts at 1.94 million, and by 2000 it has grown. The population of Miami-Dade County has grown to 2.25 million. And I think what I'm going to use, so this I could say, and I'm going to call it NO. When we were doing compound interest, that would be P. And 2.25 million is N10, what it is after 10 years. And linking this back to the compound interest model, that could be A. So let's see if I had an equation that starts off with N10 equals NO times 1 plus, what do I not know? I do not know the rate. And I've got time being 10. In this case, I'm going to use the annual. As far as kind of any exponential compounding model, I'm just going to use the annual rate. So then if I plug in what I know, then I've got 2.25 equals 1.94 times 1 plus the rate that I need to find in order to write this raised to the power of 10. Well, if I'm going to solve this, I can start off by dividing both sides of this equation by 1.94. In other words, I take that 2.25 and divide it by 1.94, and that is going to equal 1.15. May have had more decimals on it other than that, but I stopped with that. And then I've got 1 plus the rate raised to the 10th power. Well, if I want to get that, to deal with that 10th power, then I need to take the 10th root of both sides of this. 10th root of 1.15 times the 10th root of 1 plus r raised to the 10th power. Taking the 10th root of that serves to cancel out the 10th power. And the 10th root of 1.15 is 1.0149 rounded off equals 1 plus the rate. And then if I subtract 1 from both sides, I end up then with 0.014. Well, let's just do it 1.049 equals the rate. And maybe I want to round that off to 0.015 or 1.5%. So we've got a rate of growth of 1.5%. All right, now I can take that information and we can then build an equation of this model of growth. And let's just say that this is then N equals 1.94 times 1 plus, back to the decimal, 0.015 raised to the power of t. And I can use that to predict, to try to find when this population is going to go to million. And for that, my friends and neighbors, countrymen, I need to go to my calculator. So there is my exponential growth equation. All right, so I'm over here on my calculator, and I'm going to go in here to y equal. Let me clear out what I've got in here that I've used here previously. And I'm going to enter that exponential growth model, which was 1.94, right? Yeah, 1.94 times 1 plus, and I could do all that together, 0.015 raised to the power of x. Uh-oh. I gotta hit caret x raised to the power of x. And I'm trying to now find, okay, at what point, how many years out is this going to reach before this population reaches 2.7 million, I think it was, or approximately that. And I could hit the graph button and look at the graph, but I think I'm going to just go straight to the table. And so I'm looking for what number is x when y equals 2.7. And so I hit the table here, and then I'm just going to start scrolling down. There's year 10, 2.25. That was a number we were given. I got to keep scrolling. Year 22. In year 22, it's going to be 2.6919. If I rounded that, that'd be 2.7. So we started at 1990, and 22 years from that would be 2012. So I could predict that in 2012, the population of Miami-Dade County, based on the information we had, which was both the population in 1990 and the population in 2000, we calculated what our growth rate was, which was 1.5%. And then I could predict that Miami-Dade County would grow to 2.7 million, 22 years from 1990, which would be 2012. Shazam.